thank you very much for the introduction, and also just thank you for the workshop. It was a lot of fun. I will keep this short enough that we can all leave before they kick us out. So, yeah, what I will present is first order conditional model logic. Like I said, this is definitely work in progress. Maybe you're a bit confused by the title because there's not so much unified thing as first order conditional model logic. So what I will try today is introduce you what I mean by that and how to tackle this topic. Wait, where should I point the clicker thing? It doesn't work.
That should be it.
You know?
Now?
Yeah.
Yeah.
So yeah, it's an introduction. The first basically 67% is about first order model logic in general. You see which problems there are, and I want to show you that the same problems happen in first order conditional model logic. Which is the last part where I explain shortly what is conditional model logic and how to tackle this in so this is what I just basically said, but there will be an introduction to the model logic and first order logic, how to combine those two, the obstacles that come even in first order model logic already, and then I will go to the conditional part. I guess again, it's work in progress. If you find something which I think everything works out perfectly, but if you find something, please let me know immediately, then we can discuss it afterwards. So yeah, just a quick rehash on model logic. I thought I'll just do it because maybe someone is not familiar with it, right? You know, model logic extends classical propositional logic in general by introducing modalities. Something like necessity and possibility, but there's many different model logic, as you know, right? There's deontic logic, which is about today. We talk about obligation and permission, and so on. In general, I will first part keep it simple for electric modalities, so we'll talk about necessity and possibility. And usually in the propositional case, right, we have that box P means it's necessarily the case that P, and diamond means it's possible the case that P. And in the propositional case, everything is more straightforward when you know, right? They usually use cryptic semantics. So we have a set of worlds, we have a relation on the set of worlds, and we have an evaluation function which assigns each propositional variable a subset of the worlds, which tells us which formulas are true at which world, and the relation tells us which box formulas are true. That's again a recap. I'm not sure if anyone maybe are familiar, but it's important for the next step, right? So the first thing you'll know from classical propositional logic and model logic usually based in the way in cryptic semantics that box phi is true in a world if with every accessible world the formula holds. And we have this standard notion of validity, so I will also focus on a very simple case for this talk. Something is valid if it holds in a classical model, so in every world, in every model. It's associated. Oh yeah, a big part of this talk is that we're talking about because this is the main topic in first order model logic, talking about soundness and completeness. So it always is associated with a proof system. In this case, we know, right, the propositional system K, which extends propositional logic by the rule of necessitation and the axiom K. And in regard to the class of all crypto models, this is incomplete, and you would be able to extend it very simply by adding just other axioms and the associated properties on cryptic modalities interpretation. So proposition is clear, right? And we all know also classical predicate logic, which means now we are in the first order setting. So now we also have quantifiers and predicate symbols. I will also keep this simple in this case, so we'll not add constants and function symbols, but one could without any big problem. So we focus on variables and predicate symbols alone. And we also know classical predicate logic, right? So what can we do now? We kind of got predicates with variables, and we can same connect this as before. And here is the main important part, because this will the thing that will be complicated when we go to the model setting is, right, predicate logic is the logic of substitution. So now we can substitute variables with each other. This is just very formally, quickly. It's stuff that you know, but just that we also have it on the board. How the substitution works, the formula means that in this formula we replace x by z, which just is inductively defined. And the main idea is that we are careful with the substitution in the sense that we don't replace accidentally bound variables. So if a formula y is bound, we don't replace it, we just keep the formula the same. And also what we are careful about is if we replace inside the formulas, here, for example, x with z, we do not replace with something that then gets bound by an outside quantifier. So in that case, if this happens, we replace it with a new variable before. So the main idea is the substitution does not in general change the meaning of it. How do standard first order models work, right? We have an interpretation function, it's interprets as every n predicate symbol to a subset of the domain that we have here. And we have a variable assignment which assigns us each formula of the domain to each variable to an element of the domain. And we have the so-called X variant, which basically is this, which will give me two variable assignments. One is an X variant of the other when they are exactly the same, but an X they may behave differently. With this, we now can easily define two conditions for the quantifier. So when is for all X phi true under variable assignment G, basically if we can replace the assignment of X with every element in the domain, and the formula states true. Very simple. So I think for now, model, propositional model logic, first order logic. You have seen nothing new yet. I just want to recap that we can now go to the first order model logic case. Okay. Any variation so far? Anything here? No, right? So, yeah. So, and of course, like I said, we talk about we will talk about completeness. What we know from first order logic, there are some classical abilities. So I will keep everything classical in this talk. That means the quantifiers will behave classically, which means we basically have those two, this axiom and this rule regarding the quantifier. So if for all x phi holds, we can replace x with a new variable, and this implication will always hold true, which is called universal instantiation. And if it's if we can derive phi plus psi, and x is not free in phi, then we can derive phi implies for all x psi. Those rules together, usually in the first order case, will give us a complete system, and we have some classical validity, we know from that, right? So nothing here is out of the ordinary, but we can derive this if you have a propositional case and the language with those two axioms will extend. So now, what is now first order model logic? I mean, the answer in general is simple, right? It's a combination of predicate and model logic. So two things you just see we put together. So in general, you could say, yeah, combines quantifiers and model operators. As the quantifiers now can range over all sort of things like agents or actions. So we can talk about this action has performed, or this agent does something, and this agent does something. And the nice thing is now it should be able to express first order model logic, should be able to express quantified statements in a model logic setting, which is different from the propositional case. So some examples here. So for example, it's possible that some students have failed the math exam. We could express as it's a possibility, right, that there is someone who is a student and has failed the math exam. If we go to the deontic setting, we may be able to express something like everyone should treat everyone with kindness, right? Every agent has the obligation so that everyone is treated with kindness. Or the last one, someone is permitted to access the server. There exists someone who has a permission to access the server. Maybe already here you're questioning a bit, right? Intuitively, why they put stuff exactly like this. And this is a bit the part about first order model logic. The placement of the quantifier sometimes seems strange, and one should also be careful, right? For example, this one. Maybe you disagree and say, oh, I should have put for all x here, or I should put this for all x here, or I should put the like, seems a little arbitrary what I did here. The point is yes and no, we'll see, it depends on which kind of logic what you're using. And in the conditional setting, it will be straighter. So one could classify first order model logic basically by two approaches. So if you go to the literature, you can find two different ways. It was very confusing for me when I started out working in this field. Sometimes it's like purely syntactical, basically, put first order axiomatization together with propositional model logic. And the other one is more a semantic approach, where we define a nice quantified model logic and check which axiomatization holds there. So overall, we have to be careful. This is not, that does not will end up in general with the same logic what I want to show you. So one for like syntactically, one would say, okay, what you've seen before, we have seen the model logic K, right? And we let formulas now be first order or predicate formulas, and we add the axiom and the rules that we've seen for classical first order quantification, and see which kind of logic this develops, and see if the semantics fit. And the other approach is basically we take cryptic semantics or the semantics you want to use, also neighborhood semantics, and extend this to the first order level in such a way, and see if this still satisfies the classical rules that we have. So the first thing we're now looking at is actually logic. This is first order cryptic model with constant domains. That's probably, if you have seen model logic, first order model logic, yes, you have seen exactly those, and at least you have seen exactly those, and you will see in a second why, because it's a nice extension for first order model logic. So what we do, we have language as expected, we have variables, predicate symbols, logical connectives, a quantifier, and now so on. And the formulas are defined with predicates, negation and boxes, the conjunction, but also now we can quantify. So here, this could also be a model operator, and it could contain a model operator. Same here, this could contain now a quantifier. So constant domain models, like I mentioned, are the most straightforward first order extension of model logic. And they behave very similar to propositional cryptic models, but you see here, basically what we have done, we have replaced the evaluation function of the domain and interpretation function. So we have combined what we have seen before from the propositional model logic case and now the predicate case, and replace it accordingly. So this behaves exactly the same like this in propositional case, like this in the quantified case. And we have the properties again combined for the propositional and the first order case. Same goes for the variable assignment, so nothing this here. I'll just put it on the board again. How do the truth conditions now work? Okay, you see the first thing is exactly like in classical quantitative logic, but here when we have now the box, what we basically do, we check, given a certain variable assignment, we check that in all adjacent worlds the formula holds according to this variable assignment. So we fix the assignments first, and then we check if it holds in all adjacent worlds. Below is exactly as you would assume it. So now just do the combination of quantifying and model logic. So we say it's true in the world that it holds for every assignment. It's true in the model that it holds every world. It's true in a class of models if it holds every model. And generally, the formula is valid if it's all of those class of all models. So draw something up here, but like this looks exactly like it's done in the position case of every world. And we check, and if in every adjacent world the formula is true. I think I put an example here, right? So very simple, I have a world W which sees another world V, and this world sees itself. And we could check if which first order model logic formula now holds. We put X to A in the domain and Y to C. For example, we can see that box for all X Bx does not hold to the world W. Why is this the case? Because if we start with world W, we'll check if every adjacent world satisfies for all X Bx. Okay, we are at the world W. What does this mean? Which world do we need to check? We need to check the world itself and the world V. But what is the problem? The problem is that at the world V, for all X, Bx does not hold, right? So we don't get box for all X, Bx. Same if you go the other direction. So if you now first check, okay, for every element in the domain, does the box Bx hold? No, because again, the counterexample is A, because if I take A, I cannot get box Bx to hold, to replace X with A. For C, for example, it will work, right? Because Cx counts for everyone. Maybe here you already see, okay, there seems to be some kind of connection between the quantifier and the box in this kind of semantic. We will see this in a second in more detail. But yeah, that's the idea, and this you can do now because of time and existence and so on. Let's give an example that is not just mathematical. Let's look at an example like, for example, a coin flip example, right? So let's say player A bets heads, player B bets tails on a coin flip, and now you give me the statement, one player necessarily wins the bet. How would you write this down? So let's say f of x stands for x wins the bet. again, we have the two states. In the state W, A wins. In the state B, B wins. Those are my two players. And I can now nicely say, okay, at the world W, A wins because the X is sent to A, and the world B, B wins. I've made it simpler here now for basically also using different variables, which means in both worlds there exists someone who wins, namely here A, here B. So I can formulate this as necessarily that someone wins the game, right? But look at the other one. This is not the case. Why is this not the case? Because this would mean I can find an element in the domain which necessarily wins the game, right? So that would mean I can find an element here, either A or B, such that box will hold for this formula. Why is this not the case? Well, if I choose A, I can find a counterexample by this person not winning in the world B. But if I choose the world B, I find a counterexample in that one. So here we have necessarily someone wins the game, but it's not the case there is someone who necessarily wins the game. Good. This works nicely, and this is in general like a way to extend modal logic to a classical with classical first order quantification. You can easily show that the axiom rule that I mentioned before are valid. So for the representation, also evidence domain is easy to check, the same which we can do with the rules. So a way you first would say, okay, now we have done what we expected to do, right? We combine modal logic and first order quantification. Is this now the axiomatization that you find? So this is the axiom of K. Those are the first order axioms, and those are just the rules that we have seen from first order, correspondence, and again modal logic. Are those not all? Is the question. If we put the semantics together, and then we put the proof system together. And if I put the question here like this, guess the answer is no. What is missing? What I've seen, what may have been too much. So you can easily check that this is sound, right? Every rule here, everything that is derived from this proof system is valid in the model, right? Because we have seen classical quantification works, the rules K is easy to check work, and the rules of Field work as well. But the models that we created are a bit too big because we basically threw them together. And namely, what the models do, what the proof system doesn't tell us, is how the interaction between quantifiers and model operators work. Namely, this is not complete. So we have something that is valid in our models, but it's not derivable here. I hinted on it before. Basically, it's interaction. Those you have probably seen, it's quite famous, right? It's called Barkan formulas. Exactly what Ruth Barkan tells us here. So for all x box implies box for all x. They are named after Ruth Barkan Mark, which is studied in the 20th century quite a lot. So actually formulas schematas, right? Because it's defined for not just one formula, but for all our formulas. They're basically defined the following way. Barkan formula is when I can do. Some people say pull the quantifier inside, others say pull the box outside. I'm not sure what you would like to say. Well, I would more say the Barkan formula tells us that we can pull the quantifier inside the box, and the converse Barkan formula tells us that we can pull the quantifier outside the cinema of the quantifier. So if you put both of them together, if your system satisfies both, you basically can say, okay, the box and the nullosity quantifier commutes. It doesn't matter where. What I've mentioned at the beginning, we saw it, right? So we can switch out a model operator and do a quantifier. And I said, okay, this is missing from our proof system. First, I'll mention that this is valid, right? Because otherwise it's not missing. But we have seen this in an example before. The point is, it doesn't really matter if I first check every element in the domain and then every adjacent world, or vice versa. Because if I first go for every element in the domain and then every adjacent world will come up with the same result if I first go to every adjacent world and then every element in the domain. Because the domain is independent of the worlds, right? I need to check the whole domain first. So those two things are equivalent in the models I just presented. And these are both directions in one way, right? So one is the Barkan formula, the other one is the first Barkan formula. And they're not derivable, but we will hint that the Barton formula is not derivable. The Common Barton formula is derivable. We see this here, right? So for all x box phi implies box for all x phi in the system I presented before. It's a combination of universal instantiation, the rule of instantiation, k modal exponents, and the application of the universal quantifier introduction. Maybe I will get through it, right? This is universal instantiation. We just replace for all x phi x with the variable x here itself. Then we box the whole thing with the rule of necessitation. With the rule of k, we can distribute it over the implication. And then we apply all exponents. And the last one is here. This rule only needs that the thing on the left does not have x as a free variable. Since it does not have x as a free variable, we can put the universal quantifier in front. We've seen, the common Barton formula actually is derivable with classical rules. But the Barton formula, so it's the other direction. No. I switched it up, right? Accidentally. Yeah, sorry. This should be exactly the opposite way. It is not derivable. And the Barton formula, we will see this on a later slide. So now it's just a claim that I cannot derive it. We will see it's actually not derivable in the system. It may, although, be derivable if we add some more properties to the model operator. For example, if we add the x and b, which says phi implies box diamond phi, which is the x-related symmetry, we would derive Barton formula. And so it doesn't have to be always added. It depends on how strong the model. So this is now for imagine we're still in the classical first order model logic sense. This is now a complete system. Has been shown, one can derive completeness here if one adds the Barton formula. Okay, this is not sound incomplete. So everything derivable in the system is valid in the model I presented, and everything valid in the models can just be derived from the system. So, okay, a straightforward extension putting stuff together. One needs to accept the Barton formulas as we have just seen. Before I now go, okay, what is this? Why I have to be careful with the Barton formulas, and then we could go to the conditional stuff. Let's firstly discuss what does the Barton formulas even mean, right? Because one could say, okay, right, that's the thing that we need. We just throw it in there, and there's no problem anymore. It really depends, and as we've seen in the beginning, how we want quantifier placements to behave and what they should mean in a model logic sense. Namely, in here it comes down to the difference between a DRA and a dicto reading of a formula. So if we have quantified model statements, they're usually a good tool to formally distinguish between a DRA and a dicto interpretation of a formula. What does this mean? DRA talks about the thing itself, and the dicto talks about what is said. So the array formula talks about, for example, a specific person who has a necessary property, right? And about what's being said means it's necessary that someone has this property. So the dicto is more like a model statement, which we can do propositionally as well. And the array is more about an agent or about an action ascribing it a model property. Let's go back to our example before that you can see the difference. This was the coin flip, right? There exists someone who necessarily wins the game is a DRA interpretation. Because it means there is a person who has necessarily a property, which was the one we don't want to hold in this example. And the other one is a general model statement. Someone necessarily wins the game, right? It doesn't talk of a specific person, it's more like necessarily that someone will win. So we see there is a difference when we come to quantifier placement. At least we not go directly to universal, but we have to be careful where we want to put this quantifier, because this is exactly what first order model logic can do. It can very nicely distinguish between those two readings. But if one now adds the Barton formulas and the Commerce Barton formula, we basically lose this distinction when it comes to universal quantifier and box. Not only that, it also comes because of the duality of existential and universal, and the duality between diamond and the box. We also lose it for the existence and the diamond. So you can very easily derive Barton formula is equivalent to diamond exists X implies exists X diamond. So basically the opposite version for the box. There's some famous examples where this is quite problematic. Fought for some examples, then I came up with my own because I found it a bit funny. Let's look at this. Let's say we took diamond as possibility. So we have a statement, I could have a child. So last time we visited, my grandma has reminded me of that, right? I'm old enough, I could already have a child. So all the time I was reminded. So let's say CX, X is my child. So an agent, check if it's my child. Let's look at this statement first, right? Diamond exists X CX. There is a possible scenario in which there exists someone who is my child. That's basically, I think that's the interpretation that you want when I say I could have a child, right? You can imagine a scenario where I already have a child. It's a possible scenario. That's the deductive reading. And now think about the opposite, right? If I write this, there exists someone who has a property of possibility in my child, right? This is something completely different. Well, I hope this is not the case. Like there exists someone such that it's possible that they are my child, right? So we have to be very careful. This is a theory reading of this statement, which is of course right. But the button will tell us they are the same.
We cannot upload this to YouTube because Tanya is gonna hear.
So we have to be careful just to throw the Barker formulas into modal logic, right? So probably we should get rid of them when it comes to certain readings. Possibility is one of them. But you can imagine very similar examples with deontic logic and so on. Same reason goes for the Commerce Barker formula, which is less controversial, which is actually there already. I will not talk about this today, so there's other ways, although this may be problematic, but at least the Barker formula, don't always add it. So the question is now, the formula system I presented before, I claimed that this is independent of the Barker formula. So that means it's not derivable. Yeah? How does one show that something is not derivable in an axiomatic system? You have to find semantics where all those axioms, this whole system is sound, right? But does not validate the Barker formula. Because this would mean the system is sound, everything which is derivable is also true in the system, but if it's not true in this system, it means it's independent. And the point is there are such logics. This is what is called increasing domain semantics, which is how much time do I have left so that I know I can go to the conditional?
30 minutes.
Enough time. We're going to go to conditionals. So the idea is that this is something we can get rid of in general without problem. We just have to be careful how we define our semantics. Namely, which is called increasing domain semantics. So we don't want to get rid of anything of those. We just want to get rid of Barker formula. This is our classical increasing domain semantics. Everything here seems kind of the same. The only difference is now we have a domain function. So we don't have one domain for every world. We have one domain which is shared by every world, but each world gets put into a domain with restrictions, namely the domains are increasing along the relation between the worlds. So it means if W sees V, then the domain of W is a subset of the domain of V. So at worst, more people get added if you see as the next one. Nobody gets eliminated when they go to the next one. You've seen before the constant domain is, of course, is a specific case of this one, right? The constant domain basically everyone shares the same world, and now we are increasing. There's an important part of that. It's not only that, oh, we don't want to kill anyone accidentally, we go to the next world. It's well, like we'll think this is actually necessary. Okay, I don't have it in the slides here when we get rid of this one, but the point is if we get rid of this one, we will have to get rid of some classical first order axioms actually. But with only this one, we can get rid only of the Barker formula. So the interpretation here is also assigned to the world. So if an element in the domain holds has a certain property at W, this can only happen for elements in this domain. So right, it means we cannot have that something has a property which is not in it. So the definition here is now adjusted. We have the the variables get assigned to elements in the domain, which is a variable assignment at a specific world. Something is called an X variant of G at this domain, exactly as what you expect. So it's the same variable assignment. X may take a new element, but the point is that the new element has to be an element of the domain of W. With that, we can adjust now the quantifier, namely that for all x phi holds if for all elements in the domain of W holds, right? So it does not check the whole domain, it only checks the current domain. So what is the difference as before? Before we had to check also the people of the other domains, which didn't matter because they were the same. But here we don't want to do that because we don't want to actually accidentally check someone which is not captured by of a quantifier. Imagine this would be the case. Let's imagine for all x would check an element of v, and v does not exist at W. This means for all x phi may be true, but phi for this element may not be true, right? So because you don't capture every element. This is the restriction to place it, that we keep everything classical. See here the failure of the Barton formulas now. We have an increasing domain, so A holds true at W, and A and B hold true at V. Both have the A has the property A in both worlds. We have for all x box for all x box AX. Why is this the case? For every element at W, which is A, box AX holds, right? This is only the element A. I should have chosen capital A, not capital A. So if A of the well W holds a program, that's the case, right? But we don't have box for all x AX. Why we don't have that? Because if you go to an adjacent world for all x, AX may not hold. Because if I go to the world V, for all x, AX does not hold there. Because not all elements of this domain satisfy A, right? So this means here we can see the failure of the Barton formula, right? Because universal quantifier outside works, universal quantifier inside doesn't, so we don't have simplification. So this is now semantics that shows the Barton formula is actually independent from our first order axiomatization. Yeah, put the next slide here. Yeah, okay. The point is that it always satisfies the converse Barton formula is because I mentioned before it's derivable for classical axiomatic rules. Maybe you should mention because I want to mention the conditional space as well. This means if one wants to get rid of the converse Barton formula, they have to get rid of one of those things, right? Classical rules for quantification, or maybe K has to be restricted, otherwise you can always derive it. This means if you want to get classical quantification, you need the corresponding. And the reason basically why this happens, just as a more direct explanation, is what does it mean for a formula if you're able to be valid, right? If you have an Hilbert axiomatization and we derive for all phi x, this is usually understood because of the introduction of the universal quantifier as for all x phi x. But box, for that reason, box phi x is understood for all x box phi x, right? So this means the converse Barton formula is indirectly already there because as soon as we have box for all x phi x, we need to fill basically this void to have it that it's already box phi x must be true. It's maybe a little bit, or maybe it's not the best explanation, but is that indirectly, even if you change the proof system, this is something that always drops out of that. So it is, you really need to make other interactions not happening between quantifiers and boxes to get rid of this formula. One of them would be to break up basically universal instantiation, what I mentioned before, so the quantifier doesn't capture every element, but then we're not classical anymore. I won't go into that, but there's also logic of that, right? So finally, now I'm going to first to the conditional model logic. So we have you've seen what I want to do with this first, and the main part is you see just extending model logic to first order setting creates a lot of problems, and we have to be careful about a lot of things. And now we make the model logic behind it a bit more complicated, namely now we go to conditional model logic. Propositional conditional model logic, there's also not one unified thing. Maybe you all know some different ones, or maybe you don't know conditional modal logic at all. But what is the main idea? We have like a conditional operator which talks about under A, B is the case, maybe because of we'll see this later, but geometric reasoning. So given phi, psi is obligatory, or counterfactual reasoning. In the normal case on phi, then psi is the case. But the point is that this should usually be used. Otherwise we could just use implication, right? The main idea is that we should use a non-monotonic operator, so that's why it's mostly introduced. So even though phi, given phi that psi is the case, it may not be that phi and chi given psi is the case. Usually it's non-monotonic. You cannot just add stuff to the antecedent. This you could also do with an implication and a box operator, right? But this is exactly what usually is there to be avoided when we talk about conditional modal logic. Let's look at a specific one that I want now to extend to the first order level. I like the ones from preference logic. Maybe people may be familiar with it when they work in geometric logic. That's quite what's common general reasoning about preferences. So that's when we have semantics that are based on standard crypto models, and the words are ordered by preference. So W may be preferred to V, and we say a conditional holds then if psi holds in the best phi options, right? So that doesn't mean that every time we have phi, psi holds, but in the best case that you can imagine of phi, psi holds. We'll see the semantics are in the next few slides, but this is the main idea about preference semantics. They're not the weakest conditional logics. We can make it definitely weaker. They're very weak conditional logics is basically say, okay, phi gives you psi, and you have not even an extensional and antecedent. So even if the formulas are equivalent in the whole model, they may not satisfy the same properties here. But I thought I'll start with those also because I've worked with those in the past. They don't satisfy many properties, so this is a good starting point. People familiar with geometric logics know the aqueous system or such logics. So I will introduce them and how they work. The aqueous systems are organic geometric logic. We will talk about obligations and permissions, so they're often used in law and in legal reasoning, but also in like in obligation, you usually see many applications in AI and ethics. Usually you want a non-monotonic obligation operator. Namely, there's a lot of paradoxes when it comes to monotonicity. We the Gentile paradox, if you know, and many others. I don't want to go into details because it's not the point of the talk. It's just, okay, we want to avoid that. For example, if phi and psi is obligatory, you don't in general want to have that phi and psi, then phi and chi and psi is obligatory. When you put here the modal operator, for that in the aqueous systems, to use directly the adic operator. Be careful now. I didn't want to change this for this talk because otherwise, when you know, read up the aqueous system, you're confusing. They're read from right to left. So, given phi, psi is obligatory. And this is an operator that doesn't satisfy monotonicity. So even if we add more conditions on the antecedent, it may not derive the same obligations. Or and what's same with the aqueous system E, F, and G is using, we have the same properties. E is the weakest of those, which is the one I will be focusing on. And the main idea is that they extend propositional logic, similar like modal logic do with an adic operator and a box operator. How do they work? So this far everything is the same. We have worlds, but we have an ordering and an evaluation. And the idea is that phi as psi is obligatory under phi, if in the best phi worlds psi holds. Very simple case. So the arrow points usually to the worst world. So in this case, B is the better option, right? Phi and chi hold here, and phi and psi hold here. Let's look at an example. Let's say you have friends over as phi, psi is you cook dinner for them, and chi is your kitchen is on fire. So one way, okay, it's nice if you have friends over and you cook dinner for them. Also, right, so in the best phi scenario you can imagine, you cook dinner for them. This is this scenario, this is the better one, right? Those are both phi scenarios. This is the better one. It checks the best option for this one and checks if psi is true here. yeah, that's good. So we're obligated to cook dinner for our friends when they're here. But now we're in a scenario where we have friends over and the kitchen is on fire. Now, well, this is a sub-ideal scenario, I would argue. So we are in this case, right? Because this is the best side case. It's the only fine and kind case, which is not a subset of side. So this obligation is not hold. It's a very simple example, but you can extend this to many different logic. So the private logic are quite extensive. We can have multiple layers and so on, but you see how the normal intensity works, right? This is an maximization of such a logic. It looks big, but it's actually quite simple because the only thing that it says here is, oh, we have a monotonic consequence, right? So if something gets implied, then the first thing implies the second thing under the same condition. And we have, for example, an extensional antecedent, which means if two things are equivalent in the whole model, then I can replace them. But that's basically the only thing. You cannot generally add stuff to the antecedent. Now we want to put this to the first order setting. So we put the same thing as before. We take the logic, now we're going to get an operator. What I mean here, this could in general also be an implication when we want to capture something different than obligations. And now put quantifications there. So far everything is the same. So we have the Eric operator and quantifiers. But already the constant, and that's the main point, like already the constant domain extensions, one has to be careful. Namely, if we extend this now as before, we have the preference relation here. And we have to be very careful how we define the conditional. So my idea would be here to keep classical first order axioms, do the rest as before. Don't be confused with this. This just basically means because in the Aquis system, the box works as a universal quantifier. So it checks everywhere else. It's like an S5 modality. But the interesting thing is the obligation. So we take the best cases where phi holds under this interpretation G, and there should be a subset of psi, where phi is the truth set for this variable assignment, and the best cases are basically the maximal cases. Is exactly the same as in the propositional case. So it checks all the phi cases which do not get trumped by another phi case under the same interpretation. With this, we can now let me put a slide. Okay, sorry. We can easily check that this satisfies exactly the same axiom. So the first order version of this axiomatization will again be true. But again, we may be adding too much. Namely, the first, we definitely destroy some interactions which are different from material implication, but we also add some stuff. Let's show things that are interesting properties, but that's just that this addition do not happen, which usually happen in material implication, namely, distribution of universal quantifier over material implication. This does not hold in such a non-monotonic operator. You can finalize count, for example, but basically the idea is, right, every best phi case may be a psi case, but it doesn't mean if you go to the best for all x phi cases that all for x psi hold there, right? Because every time you're in the best phi case for every element, it may be a psi case, but if you go to a set to a world where for all x phi holds, this may not be an individual best case for each one of them, right? So this implication doesn't hold. You can easily build a counterexample with a big enough model. Other things are also untold, right? It's similar as we've seen before. So we cannot pull the existence outside of the operator, and this means that, like we know with material implication, even though we have A implies exists X B, we cannot have exists X A implies B, even if phi is free here. So there we can also build some counterexamples. So it already behaves quite different from material implication. But the conditional version of the bargain formulas are valid again, as we have seen in the model case before. So in the monadic case before. So I call this now my own name. Maybe there was conditional bargain formulas and conditional converse bargain formulas. The names get quite long. They are valid with the assumption that X doesn't appear freely in phi. So a first order extension of such a logic, and this would happen in other conditional logics as well, must include the Barkman formula if you don't place any extra restrictions, because basically as soon as you have something like a monotonic consequence, it will happen again that if you have constant domains, they satisfy the same if we put the universal quantifier outside or inside. So this system is sound, and the Covers-Barkman formula, the conditional Covers-Barkman formula is derivable. You can see this here. So this seems like a lot, but basically the only thing that we would need here is that, as I mentioned before, the Dyadic operator be monotonic already derives as the conditional Covers-Barkman formula. And in the last step, we need actually that psi doesn't have x free, because otherwise we cannot put the quantifier there. So for a conditional model logic, there's exactly the same problems that happen. Basically, we have to be careful that where we put the quantifier. But this case here, I checked that it is sound, and I say now I have proven it, but I need to recheck it because it's very recent and I'm not 100% sure. I'm pretty sure the system is complete. Also, I have to mention the Guido because he mentioned last time that another system may not be complete. So I'm pretty sure. I've checked and the proof seems to work. I will say I missed some introduction, but this is quite interesting that it already works with such a simple addition. And I can also think extended with F and G. F and G are those extensions of the Aquis system where you just for F you add an axiom, for G you add another axiom, so there shouldn't be a problem. Which is quite interesting because those systems are very related to other first order conditional logic, like the KLM logics and so on. So we could try to do this as well. So if you're interested in your favorite conditional logic to be first order, write me an email and we can discuss it and see if this works. One thing I'm very puzzled though by is that you've seen before very easily with the extension, with the increasing domains, that we can prove that the Barkman formulas are independent in the monadic case. Here, this doesn't work so easily because here the conditional already checks up and down basically because it checks the best option. So getting rid of it just for the conditional is straight because for the box you can derive it because we have this 5 modality. So here we would want, if this is really independent, it sounds, so we can add this role. If it's really independent, there must be some very weird semantics out there which basically don't satisfy it for the conditional, even though they are satisfied for the box. But it would be interesting to check and show how this is really independent. And it would be interesting to check if we can do a very similar thing for other first order extensions, also when we have like non-global conditional operators. But this now is very simple. We have basically only one structure. But there are other conditionals that basically if you go to a world, it only has a specific ordering there. So the conditions are not global operators, so they change from world to world, so that there may be some a bit different interactions. But I think the overall interaction would exactly be the same. And for that, it would be interesting to extend the language with constants, functions, symbols, and descriptions, and equality. So equality is its own right, a bit problematic, and that's stuff for now. But this already we have done a bit. This was a paper that I've done with Sandeep at the beginning of my PhD, where we basically looked at the first order extension, a non-classical extension, just checks what works, what doesn't work. Already there's a lot of weird interactions for conditional logics. But this was now focused specifically on the conditional, that's why it's something new. And that is basically what I want to make sure. The last points are also studying non-classical personalization of the system, where basically we can make something with only the Barkman formula valid or only Converse-Barkman formula valid, so both go in both directions, like it would be in one other case. By the way, acknowledgements. Thank you for the Mosaic project, to the Mosaic project for also allowing me to be here. They're also funding my trip, and the logic projects. Logic methods for the explanation, also for them doing this deontic extension, which I'm also partly funded by. This is some additional material. I'll end this whole thing with a selfless shame plug because this is a seminar that I developed focused on first order model logic. If you're interested, visit the website and go there. We had last year a lot of interesting talks. It was a bit stopped at the beginning of the year, but it will start again after the summer now. And if you're interested in general about this topic of first order model logic, just join. Okay, I think that was it. Yeah, thanks.